So Nathan received his bachelor's in math and computer science from UC Berkeley, and then he went on to receive a PhD in operations research from MIT. Following his PhD, he was a visiting scholar at USC's Department of Data Sciences and a postdoctoral associate at MIT. Nathan is now an assistant professor in the School of Operations Research and Information Engineering at Cornell Tech. He's won multiple awards, including an NSF Career Award in 2019, I think. His research interests include optimization, especially under uncertainty, causal inference, sequential decision-making, and algorithmic fairness. He's a prolific scholar, regularly publishing impactful work in top venues. And I follow him on Google Scholar, and I always get excited when he puts out a new piece. His work elegantly fuses ideas from optimization, statistics, and causal inference, and I learn something new every time I read one. So Nathan, we're really lucky to have you today, and I really look forward to hearing about your work on smooth contextual bandits.
Thanks, Alex, so much for the very kind introduction, and thanks everyone for having me here. It's a pleasure and an honor. So I'll be talking about work that's joined with my students Yichun and Xiaozhe on smooth contextual bandits. And I thought I would start by just talking about what's a contextual bandit. So we're starting on the same page, and then talk about, well, what's a smooth contextual bandit? So a contextual bandit is essentially a model for decision-making in an uncertain environment, where we are learning about the environment at the same time that we're making decisions in it and collecting the rewards corresponding to the decisions that we make. And the model goes something like this. For each time step, little t equal to 1, 2, etc., we're going to encounter a unit drawn from some population of units described by some distribution p. And each unit is going to be associated with some baseline covariates xt, which are available to us to observe before we have to make the decision. These are also called the context variables. This is the context for the decision, and also n potential outcomes for each one of the actions we can take. The action we take at time t is going to be a function pi for policy of the context, because we're trying to make the best decision within the context. It can also depend on some randomization, because that can come in useful. And it depends on all the data we've seen so far. So the context, the actions, and the rewards that we saw up to time t minus 1. And this is important because this is the data that's available to us in order to learn about this unknown population, this unknown environment. After we make this decision, we get to see the reward corresponding to that action. We don't get to see the reward corresponding to the other action, and that's the reward we collect. So we get to see it, and that's also what we're trying to maximize. So you can think, just as an example in the back of your head, of newly diagnosed diabetic patients arriving at a doctor's office. Each one has some covariates associated with them, say their age, their blood pressure, their current blood sugar levels. And then based on this information, the doctor will decide either to give them sulfonylurea, tell them to diet and exercise, give them insulin, etc. And then she will see, what is the hemoglobin A1C down the line, and have we stabilized it well? And then we'll learn a bit more and know how to treat the next person better. For this talk, I'm going to focus on the case of just 2 actions instead of m actions. It all generalizes, but this will make it much easier to talk about the problem. So there's just 2 actions, -1 and +1. And again, just, these are abstract, but you can try and think about the -1 as don't intervene and +1 as intervene, for example. So how do we say whether a policy is good or not good? Well, we compare it to the best policy. What would be the best policy? Well, in this instance, where there's a fixed distribution, it's just not known, the optimal policy would be to give action +1 if it has a larger conditional expectation given the covariates, and action -1 either. So we can write the optimal policy as the sign of the effect function, which is the difference between these 2 conditional expectations. So f sub a of x is going to be the regression of the potential outcome of action A on covariates being equal to x. And then we're going to compare ourselves to this optimal policy, and we're going to say that our regret when we follow policy pi up to horizon capital T is going to be the expected cumulative rewards that we collect using our adaptive policy that at time t pulled arm AT versus the cumulative rewards that the optimal policy pi star chose. And notice that the optimal policy doesn't care about the historical data because it already knows P. So it's only going to care about the current context, and they're going to pick the action that's best for the context. Now, this is not good enough in order to tell us, how hard is a problem in terms of how big the regret must be, because I can also always say, okay, to minimize the regret, I play pi star. The regret of that is 0. So for that, we're going to define this construct known as the minimax regret, which is given as follows. It's given by some class of bandit problems, which is essentially just a class of distributions P that parameterize that problem on the previous slide. And then we're going to look for a single policy, pi, that is going to control the regret over all of these problem instances. Okay, so this is going to formalize this notion that the policy is not allowed to know the instance a priori. It has to work for all of these instances. And over time, it should learn which P is it that the super player picked. And it must control all of these regrets. Crucially, when we're restricting the set of probability distributions, we're restricting the set of regression functions, right? This is just a function of these distributions. And indeed, all we need to do here is learn these distribution functions these regression functions in order to play like pi star. So underlying this is just some sort of supervised learning problem. We just need to learn a regression function so that we can mimic what pi star does. And
okay. Yeah, so there's a question from Thomas about, could the potential outcome at T depends on earlier actions?
No, so here I'm assuming that at every time a unit is drawn IID from a fixed distribution P, independently of the past. So it's just a different realization at each time T. So this is the so-called stochastic bandit setting. I hope that answers the question. Let me know if you have any follow-up question.
I think that should be good. So Thomas, if you have a follow-up question, you can just let us know. Thanks.
So we said that underlying this is a supervised learning problem, essentially. We're just trying to learn these regression functions so that we can choose the action that maximizes them. And if we're restricting the class of problems we're looking at, we're restricting the class of conditional expectation functions that could be realizable. And we know that supervised learning over a rich function class is harder than supervised learning over a less rich function class. So intuitively, this minimax regret should have a very, very close relationship to the complexity of this function class. If we can learn these functions very quickly, then we don't need exploration, and our regret is going to be very small. And vice versa, the harder it is to learn these regression functions, the higher our regret should be. So let's try and explore this kind of intuitive idea and look at some instances of this problem that have been studied. So certain choices for the regression function class script F. So I call these regression functions. So maybe the first thing that should come to mind is linear regression. So suppose we assume that each one of these conditional expectation functions is given by some linear function. So there's a coefficient for the plus function and a coefficient for the -1 function. So we're going to look at script P consisting of distributions that satisfy this condition. So this is something that was looked at by Goldenschlager and Zevi, and they showed that the minimax regret is exactly of order log capital T, right? So this theta means it's exactly of this order. So they showed they exhibited a policy whose regret on any one instance is log T. And they showed that given any policy, there's always going to exist an instance on which its regret is at least log T. Therefore, the minimax regret is of order log T. But in some sense, in this particular problem, linearity is kind of a magical assumption. So while if you're doing offline data analysis, all models are wrong, but some are useful, and linear regression could really give us a lot of insight into the problem. Here, assuming linearity, when you're trying to say, how should we design our data collection? How should we experiment? It's a very, very strong assumption. So to illustrate this to you, consider this thought experiment. Suppose here, I have X being a univariate variable, and on the vertical axis, I have the dimension of rewards. And here I'm plotting the graph of the conditional expectation function of arm+1 given X. And I'm assuming it's linear. And I give you all of its values between 0 and 0.4. So this is trying to say, suppose I really explored pulling arm1 in these contexts, so much so that I know this function exactly. But I've never explored pulling arm+1 in the context over here. Now a new context arrived at 0.7, and I ask myself, Should I pull arm +1? Is it going to do well? Is it going to do badly? Well, what is the expected reward? Well, I don't know. I've never tried it here, but I do know because it's a linear function. Then a line continues as a line. So even though I've never ever tried arm +1 in the context 0.7, I know exactly what's going to happen, right? So in fact, you don't even really need exploration in this context because there's going to be enough randomness from the arrival of contexts that eventually you're going to see each arm in some fully dimensional set. You're going to learn that hyperplane and be able to extrapolate everywhere. So it really doesn't even have that signature exploration exploitation tension of bandits. So what could be maybe the other extreme? Let's assume almost nothing about these functions. Let's just assume that they're functioning functions. We can draw them on a piece of paper without lifting the pencil. So let's say they're Lipschitz continuous with some Lipschitz constant L. Let's say L is equal to 1. How would this thought experiment play out now? Now I give you again the graph of f +1 from 0 to 0.4. And a new context arrives at 0.7. And I want to ask, what does arm +1 do over here? Well, now I can no longer fully extrapolate. It can go up, it can go down. All I know is it has to be in a sort of cone of slope 1, but maybe it goes up, maybe it goes down. We don't know. So this problem was studied by Rigola and Zevi, and they showed that in this context, the minimax regret is of order t to the power d over 2 plus d. And d here is the dimension of the covariates x. For the rest of the talk, covariates are going to be some d-dimensional variables. And this tilde here means that it's up to polylogs, right? So no longer are we looking at logarithmic regret, and therefore we don't really care about the polylogs because the leading term is polynomial. We're just going to focus on the polynomial. Now this is much, much higher than log t. And it could be actually almost linear. If d is equal to 10, say, this is like t to the 0.83. So it's quite high. And well, how do you even achieve this optimal regret? To achieve this optimal regret is quite simple. All you have to do is the following. You take your x space and you split it up into bins. And then you approximate the effect function. Sorry, the conditional expectation functions as constant within each bin, so that the problem reduces to just playing a separate non-contextual bandit algorithm each one. So if you just play parallel bandits that are completely decomposed and you choose some optimal bandit algorithm, say UCB, then you will achieve minimax regret. So if a context arrives and it falls in this bin, you just advance the corresponding bandit problem by one step, completely ignoring whatever is happening in the other bins. So really what we see is, yeah?
So Thomas has another question. So he was referring to the previous one. So, but in the patient treatment settings like diabetes, so where you treat the patient multiple times, like it could happen like the patient's response at time 2 might be dependent on the patient, how patient was treated in the time 1.
Absolutely, this is a great question. And for now, I'm only talking about kind of one-shot decisions. So you encounter each decision instance once, and you get to make one decision. So each is independent of the past. It's a different setting where you can think about dynamic treatment regimes, essentially. And that was actually something we studied in a different paper, looking at combining the dynamic treatment regimes and bandits. It's kind of closer to reinforcement learning, episodic reinforcement learning. But it's a great question, and that's not at all, I'm not going to touch on that at all here. So I'm just going to assume you have one opportunity to make a decision in each decision instance. Great question. Hope that clears it up. So maybe, chronic diseases like diabetes, not the best example.
Okay, great. Thank you.
So these are pretty much the extremes that have been studied for this problem. So either we make this magical linear assumption that the data is infinitely extrapolatable and we get tiny, tiny regret. But to caricature the assumption that we're making here, let's say, okay, something very relevant to my life right now. We don't have vaccines for kids under 5 and for COVID, because we didn't have good experiments on that just yet, or we have some experiments but not enough. And here this assumption would say, okay, we've tried the COVID vaccine on adults, we have experiments on polio vaccine on kids, we're just going to extrapolate from these 2 cases, we don't need experiments on kids, we're done. But that is, of course, not how we do experimentation. We don't trust that. That is not how we direct exploration. And indeed, what we get here is less of a bandit because it doesn't even have that exploration exploitation tension. On the other hand, we've seen that people have been looking at these very, very weak assumptions, assume almost nothing, like the data is just, the functions are just Lipschitz, the data is correspondingly super local, no opportunity to extrapolate, and we'll get very large regrets. And the optimal algorithms don't really leverage contextual learning here because it just decomposes into non-contextual problems. So this kind of hides what in the beginning seemed super intuitive, that there should be some sort of interplay between function complexity and regret. And so what I want to try and do in this talk is try to understand that interplay more deeply. So my plan is going to be as follows. I'm going to first set up what is this bandit problem that's in between. That's going to be our smooth bandit problem. And then we're going to talk about, well, how should we design an algorithm that should have low regret in this setting? So here in part 2, I'm essentially going to describe the script P that we're going to tackle. And then I will talk about how we can bound the regret of this algorithm, and thereby we will characterize the minimax regret in the smooth bandit problem, and exactly be able to see how does function complexity influence minimax regret. We're going to be able to see the whole spectrum. Time permitting, which it might not. I was thinking of also talking about a different problem, which is how do we actually draw statistical inference at the end of all of this? Because in a lot of applied settings where we do randomized experiments, say development econ, which their randomized trials won the Nobel Prize last year, there's this push to replace these with bandits because they can improve the outcomes for patients, they can improve the learning. But in these settings, we actually want to learn something. It's not just about controlling regret. We also are running an experiment, want to learn something at the end. We want to construct confidence intervals, but we've made adaptive arm allocations. So the standard approach to inference is broken. So there's a question, how do we fix that? How do we do inference after running a contextual bandit? But for now, let's focus on the smooth bandit problem. So what is this sort of problem that's in between these two extremes that render the problem somehow less interesting, less rich? So let's try and play this thought experiment again. Here we had the linear thought experiment, and here we had the Lipschitz thought experiment. What's kind of in between? Let's try this again. Suppose again, I give you the graph of f+1 everywhere between 0 and 0.4. And now I also tell you this function is somewhat smooth. It has, say, 3 derivatives. So again, a new context arrives at 0.7, and we ask, what should we do? What is +1 going to do here? So we still cannot extrapolate perfectly, but we can do a little bit better than what we did over here. So this function has derivatives, so it is Lipschitz. We can construct this cone, but we can do better than that. We can construct a Taylor approximation, say, right? So we'll have a third order Taylor approximation, and it's going to have some error, but that error is going to be smaller than that cone because it's only going to be third order now. So in particular, we can see from the shape of this curve, it can't just tank all of a sudden over here. It has to go up because it has derivatives. It's smooth. And we know that maybe over here, it'll keep going up, but we don't know what it's going to do way out there. Maybe it goes up, maybe it goes down. So we can extrapolate a little bit farther, but not infinitely far, but a little bit farther than here, but less far than we can here. So it's exactly this in-between setting. So we're going to use this to characterize the problem setting. So this is going to be the key assumption that we're going to make. So now I'm listing all the assumptions that I'm imposing on the script P that I'm going to study, the family of bandit problems I'm going to study. So I'm going to assume that for some smoothness parameter beta, which is at least 1, each of these functions is going to be beta smooth. So by that I mean it's going to have derivatives of every integer order strictly smaller than beta, and those higher order derivatives are going to be continuous. Okay, so this is somehow how I'm going to interpolate between the integers. So essentially, I'm just going to count the derivatives like we did on the last slide, but in between the integers, I'm also going to make those highest order derivatives slightly more and more continuous. Okay, so in particular, I'm going to take the fractional part of beta, and I'm going to say that those derivatives are that fractional part of beta Holder continuous, which means that they're like Lipschitz, except the power isn't 1, it's that fractional part of beta. So some examples of this, if beta is 1, then we're talking about Lipschitz functions. If beta is 1.1, then it's just slightly more than Lipschitz. It's differentiable with a very, very, very slightly continuous derivative. If beta is 2, it's differentiable with a very continuous derivative. It's Lipschitz continuous, which is like almost differentiable. When beta is equal to 2.5, and then it's twice differentiable with a half-Holder continuous second derivative, et cetera, et cetera. So this is going to be the key assumption that we're going to make. We're also going to make some regularity assumptions, which were also made in those other examples I talked about in the beginning. So we're going to assume that the rewards are bounded. Might as well assume they're in 0, 1. And we're going to assume that the covariate distribution has a density with the compact support. And on this compact support, it's bounded away from 0 and infinity. The next assumption that we are going to need to make is a bit more involved. So first I have to introduce a definition. I'm going to say that a set is a regular set if when I take any point in the set and make a ball around this point, then the intersection of the ball with the set is always going to be at least a constant fraction of the ball. So here on the left, the set is regular because the intersection is always a quarter, no matter where I put the point and how small I make the ball. Over here, the set is not regular. It has these isolated points where if I take balls around that those points, then as I shrink the balls, I get a vanishing fraction of the volume of the ball intersecting the set. Now, why is this a relevant definition? Well, I said these functions that we're going to need to learn, these regression functions, they're smooth functions. How do we learn smooth functions in offline regression? Like, forget online for a second. In offline regression, well, that's non-parametric regression. How does non-parametric regression work? We look closer and closer and closer and closer near a query point. Think about kernel regression. So in this classic offline non-parametric regression problem, if we're in this setting where we're regular, we know exactly how much data is going to be near X. It's going to be like n times r to the d, because that's the volume. If we're in this irregular setting, then we don't really know how much data we're going to have near all of these points, and we're not going to be able to achieve minimax rates. Now, we need a slightly more refined assumption than that, because in our online setting, our data collection is adaptive, right? This idea of we know how much data is near a point only makes sense if I collect data uniformly everywhere. But I don't want to do that in a bandit, because if I collect data uniformly everywhere, I will just collect a lot of regret. I want to collect data only where I need to collect data in order to learn. And if I've already learned what arm is best, then I should play that arm. I shouldn't waste time exploring. I really have to balance exploration and exploitation very carefully in order to do well in a bandit. So here we're going to need a slightly different assumption. We're going to need that the set where arm +1 is admissible with respect to the optimal policy is regular, and the same is true for the set where arm -1 is admissible. So think about this setting where the support of X is this box, and here this is the decision boundary where on the left, upper left, arm +1 is admissible, and on the lower right, arm -1 is admissible. So why do we need this pink set to be regular? Well, what's going to happen is as follows. If we're deep into the pink territory, that means we're far away from the decision boundary, and it means that these arms are nicely separated in these contexts, and we're going to learn very, very, very quickly which arm is optimal, because we only need very, very rough estimates to see, okay, this one's better, this one's worse. As we get closer to the decision boundary, these arms are going to get very close, and it's going to be very hard to distinguish, is arm +1 above or is arm -1 above? Small errors can trick us. And so we're going to need very, very, very high quality estimates. So to get very high quality estimates, we need to ensure a lot of data. If the sets are regular, that means that, say, if I want to learn arm +1 at this point here, well, it's enough to play arm +1 in this red region, and I will be able to learn it because I'm going to get like order r to the d data. If I'm in this irregular setting, however, it means that just by playing arm +1 in this red region will never be enough. I will be forced to play it in this white region, but in the white region, arm +1 is suboptimal, and therefore I will collect a lot of regrets. So that's sort of the intuitive reasoning for this. Formally, what we can show is that in the absence of the shape assumption, the minimax regret is orders larger. It's of a different regime completely. Okay, so now the last assumption that we're going to make is sort of it's more of a condition number. It's called the margin assumption, and it's as follows. So like we said, when the arms are very close to one another, it's going to be very hard to distinguish which arm is optimal. When the arms are very far from one another, we can tell them apart really, really quickly. Now, it's not possible to say that the two arms are bounded away from each other all the time. Why? Because this effect function, f plus 1 of x minus f minus 1 of x, it's a function. If it's somewhere positive, somewhere negative, and it's continuous, has to cross 0 somewhere. So it should be able to get arbitrarily close to 0. So instead, what we're going to ask is, well, how often is it close to 0? How many bad contexts are there where in those contexts x, it's really hard to distinguish between these two arms, right? So we're going to say, what fraction of context x have the effect function being positive, but smaller in magnitude than delta? And we're going to say that should be no more than roughly delta to the alpha. So if alpha is 0, this is a null assumption because we can choose c to be 1. But if alpha is bigger, then we're making some assumption. So if alpha is very small, we're saying this effect function is going to cross 0 very slowly. It's going to spend a lot of time near 0, messing us up. If alpha is equal to 1, this effect function, which is generally non-linear, is going to cross 0 in a linear fashion, okay, so somewhat quickly. And if alpha is bigger than 1, then it crosses 0 super fast, right? It jumps through 0 and spends very little time tricking us. Now, you might notice something about this rightmost plot, which is it's impossible, because if I assume that these functions f plus 1 and f minus 1 are smooth, they have a derivative, then the difference has a derivative, then this cannot happen because here, when it's crossing 0, to cross 0 faster than linear, it cannot have a derivative here. So indeed, there is some sort of interplay between the margin assumption and the smoothness assumption. In fact, we can show that if we assume the beta smoothness, the bounded density, and the alpha margin, then if alpha is bigger than 1, then this function can never cross 0 in the interior of the support. Because if it crosses 0, this situation happens, and then it's not smooth, but we assume it's smooth. In particular, if the margin is very, very sharp, it's bigger than d, then this function is like not even allowed to get close to 0. Now, this is just important to keep in mind. It doesn't really change anything for us. So all we're saying is that if alpha is big, the problem is sort of trivial in the sense that, on each connected component of the support, only one arm is optimal. So it's not really a continuous covariate contextual bandit problem. It's just a non-contextual bandit problem. We just have to figure out what is that one optimal arm. So that's not really going to matter. Our algorithm is going to handle all cases of alpha, whether trivial or not. But it's just, here we're defining a new class of bandit problems. So it's important to keep in mind what are the interesting bandit problems, where it's sort of still contextual and not so trivial. So what's important to keep in mind here is just that the sharpest interesting margin for us in a smooth bandit problem is going to be alpha equals to 1. So we're going to restrict our attention to alpha between 0 and 1 from now on. Okay, so that's the class of problems that we're going to tackle. Another question is, well, how do we design an algorithm that should kind of work in this setting? So the first thing I'm going to say is that these sort of algorithms we saw working in these extremes that I mentioned in the beginning just have no chance of working here. For example, there's no way you can extrapolate infinitely and learn a global model and not explore. You actually need to figure out, okay, here I need to explore. I haven't really tried arm plus 1. It's not enough that I only pulled arm plus 1 all the way over there. On the other hand, I shouldn't just separate this into decomposed separate non-contextual bandits, or any sort of problem where whatever I do here isn't influencing what I do here, because if these functions are smooth, then I should use data from far away because I have some opportunity to extrapolate a little bit. And if I separate things, then I don't have this opportunity to look in the bin next door. So maybe if I make the bin larger, if I make the bin larger and assume that this is just constant, then I'm really approximating a smooth function very, very, very badly. So neither of these things are going to work when you're going to need something in between that's going to extrapolate a little bit more, not infinitely far. So what I'm going to do next is I'm going to walk through each of the ideas that we had in a logical kind of order when we were thinking, well, how should we design this algorithm? And it's going to proceed in the same kind of thought process that we had, and then I'll culminate in, well, what is the algorithm? So the first idea of how we might design a good algorithm is recognizing that this is underlying this problem is some sort of non-parametric regression. So in particular, these functions are smooth. So these conditional expectation functions that we're trying to learn, they're smooth. So if we had enough data. And it's a really big if here, because that's the operative if that is the new dimension of this problem in the bandit setting, in the adaptive setting, that we have to collect data only in places where we should collect data, and we should never collect data where we should not collect data and just collect a lot of regret. So for now, if we had enough data, right, for kind of in this offline setting where we have data, a good data density where we're trying to learn things, then we can learn this function f of a of x naught using local polynomial regression, kind of one of these non-parametric regression methods. So it's going to proceed like this. I'm going to look in the neighborhood near x naught, and then I'm going to fit a degree beta polynomial to this data just by these squares. And then I'm going to apply this polynomial that I fit to x naught in order to get my prediction at x naught. I can do this at any one x naught, and then I get a non-parametric estimate for the regression function. So in this simple kind of offline regression example I'm plotting here, this is indeed close to the true regression curve that I generated this data from. The next idea is I don't really have to do that. If I have some other point, x prime, that is very close to x naught, then the estimate of fa at x naught is also a good estimate for fa at x prime, because these 2 points, x prime and x naught, are very, very close, and f itself is smooth. So it suffices to make a cover of my support and make only one estimate per element of the cover. So let me illustrate it to you. So now suppose we're in 2 dimensions. So we have x1 here, we have x2 here, and we have y on the vertical axis. And say the red dots is data that I've collected from arm +1, and the blue dots are data I've collected from arm -1. So now I'm going to construct my local polynomial estimates of each one of these regression functions. I'm going to look at their difference because I only care about the effect function. And then I'm going to clean this up a little bit. I'm going to give it color and remove the dots. And essentially what we're doing is we're not going to use this estimate that's kind of constructing this local polynomial estimate at every point. We're going to discretize it by covering, covering the unit cube by these small little cubes and making only one estimate per cube. So now I'm going to estimate my function is just this piecewise constant function. And what this does is, well, if we look at it from, my computer is stuck. I have an animation, but I think my computer is just too slow to do the animation. So I'm just going to skip it. So essentially what this is going to give us is a sort of heat map of where we think arm +1 is good and where we think arm -1 is good. Okay, here we go. So it's going to give us this sort of heat map of where we think arm +1 is good and where we think arm -1 is good. Okay, now it's gone completely berserk. Yeah, okay, hopefully now it's good. No. I'm gonna try and restart it, sorry about this.
Yeah, sometimes I think the computer, yeah, if we have a large files and it's reading, it might take a while. So maybe we can, yeah, while we are waiting, maybe we can ask if the audience have any questions.
Yeah.
So personally, actually, I'm curious. So in the step 2, when you do mention,
oh, I know what's going on. One sec, my computer is dying. Oh, my cable. Oh, it's over here. Okay, hopefully that's better.
Yeah, I think I saw that like the power, like that's a powerful. Yeah.
Okay, sorry about that.
Yeah, no problem.
Any questions meanwhile? While I try and get back to where I was. You can still see my slides, I hope?
Yes, I can still see your slides.
Okay, okay, great.
So I'm just curious. So in the step 2, you do discretization for the local polynomial regression you estimated in the step 1, right?
Yeah.
Okay, I see. So I'm just curious that would probably, it seems to me that could introduce some bias, right? Because when you are doing the discretizations, so that would probably introduce another layers of bias. So is there any particular reason for doing that? Is it for like ease for computation?
Why am I discretizing?
Right. So you already get a number like regression.
So excellent. This is exactly my next, like exactly where I was going. What is the point of discretization? So we get this heat map by constructing these estimates. We have this heat map of where we think R+1 is good, where we think R-1 is good. So what do we do with that? Well, the next idea is that, again, if we have enough data, then we can ensure a high probability L-infinity bound on the error of our estimates just by taking a union bound over these cubes. And that's why I'm discretizing, because now I only have finitely many estimates. So to get a nice probabilistic guarantee, all I have to do is union bound. So in particular, what we can show is that the probability that the error between the estimate of the regression function and the true regression function is bounded by B uniformly over all X in a region where I have a lot of ARM-A data. So if I'm only looking at that nice region where I've collected a lot of ARM-A data, then the probability that I have good estimates in that region is very high. So the next idea is, well, what do we do with that? So now essentially we have confidence intervals. Because, because if we look in the region R, where we have this nice guarantee for both R+1 and R-1, and we just assume that the bound holds because it holds with high probability, then we can essentially split this R region into 3 subregions. If our effect estimate is so big that even if we added 2B to it, we still don't reach 0, then because this bound holds, clearly R+1 is optimal. Conversely, if the effect function estimate is so negative, then when we add 2B to it, we don't reach 0, then R-1 is clearly optimal. And if it's clearly optimal, then we should just pull that arm. We don't need to keep exploring. We don't need to collect any more data. We can just, pick the arm that's optimal. If we're not sure, if we're in this margin of uncertainty, then maybe what we should do is we keep randomizing so we can learn a little bit more about these functions. And maybe in future rounds, we're going to be able to figure out which arm is optimal. So essentially, we're going to take this heat map and we're going to threshold it at +2B and -2B. And we're going to get essentially a plan of attack. In the red region, we're going to pull R+1. In the blue region, we're going to pull R-1. The effect function estimate in this region is so negative that we're pretty sure R-1 is optimal. And in this gray region over here, we're going to randomize. We're going to pull a random arm. So maybe in the future, we can learn a little bit more about which arm is better here. But there's a problem. This is not enough because there are going to be these isolated islands where we still might have not figured out which arm is optimal. So we say, okay, that's fine. I'll keep randomizing so I learn. But that's not going to be enough because if I pull R-1 and +1 just in this little cube, that's not enough to make good estimates. Because these functions are smooth, to make good estimates, I need to look far away and be able to collect data from a big neighborhood around this point. But if I look in a neighborhood around this point, everybody around me has stopped exploring. They're just pulling R+1 at this point. So I'm never going to collect enough data on R-1 to learn its value at this point, and I'll be forever stuck. And I'll just keep collecting bad regrets over here. So that's not good. So how do we fix that? Well, essentially, what we can show is that because we have smoothness and regularity, roughly speaking, if a cube is surrounded in some technical sense of what it means to be surrounded by other cubes that have already figured out that arm A is optimal, then it cannot be to sufficient probability that arm A is not also sufficiently optimal there too. So we can run a special screening procedure looking for these cubes that are surrounded by red and just infer, okay, this cube should also be red. So we're going to take this plan of attack and then we're going to refine it. We're going to iron out these isolated islands. and coalesce them into exploitation regions that surround them. And that's it. That's going to be the algorithm. So it's going to proceed in geometrically growing epochs, and in each epoch we're going to have a plan of attack. Okay, so these epochs are going to be, the first epoch is going to be 10 steps, and the second epoch is going to be 20 steps, and the third epoch is going to be 40 steps, and the next epoch is going to be 80 steps, and then 160 steps, et cetera, et cetera. And then at the end of each epoch, we're going to refine. So in the first epoch, our plan of attack is going to be randomized everywhere. So we're always going to keep 3 sets on hand. The region of the covariates where we're going to randomize, the region of the covariates where we're going to always pull arm +1, we're going to exploit arm +1, and the region of the covariates we're going to pull arm -1. We start by randomizing everywhere, and then at the end of epoch 1, we're going to fit our regression functions and try and learn, well, which arm is optimal. At each point X, we're going to fit these regression functions, we're going to construct these confidence intervals, and where it's clear that arm +1 is optimal, we're going to peel it away to the exploitation region. When we think arm -1 is optimal, we're going to peel it away to the exploitation region. Where we're not sure, we're going to keep randomizing. So maybe we learn in the future. Now we're going to play this plan of attack for 20 steps. At the end, we're going to reassess. We're going to fit the regression functions. We're going to see, okay, we're pretty sure that arm +1 is optimal here. We'll peel it away. But now there's another way to peel away these hypercubes. Another way to peel away something into an exploitation region is by inferring from the geometry of the problem that arm +1 is sufficiently optimal there as well. We can either peel away because we've learned that arm +1 is optimal statistically, or if we learned geometrically that arm +1 is optimal. Okay, and then we just keep peeling away from the randomization region. So the randomization region keeps shrinking and shrinking and shrinking with each epoch. So the last idea is, of course, to control everything just right, we have to carefully control all of the parameters of the algorithm. In particular, as the smoothness increases, we're going to need to make higher resolution estimates. So the covers that we're going to make are going to be smaller and smaller and smaller and smaller hypercubes. And we're going to need to look farther and farther and farther away in larger neighborhoods, larger bandwidths to make our estimates. The case on the far left is exactly what happens when beta is smaller than or equal to 1, and is the reason why separation into independent problems works. Because essentially, intuitively, the optimal bandwidth is smaller than the optimal resolution. Okay, so now what I want to do is I want to go through, give you a sense of the argument for bounding the regret of this algorithm. So to do that, we're going to think about 2 important events that happen. So one event is the event MK, M for many, which says that in epoch K, we have collected enough data on each arm in the randomization region. So this is going to be an event that's going to be pretty easy to guarantee because we designed the randomization regions. So we're just saying enough X's fell into the randomization region, and we pull A to be +1 or -1 occurring probably, so we can guarantee that we have enough draws from each arm in epoch K. The second event, GK, G for good, is that in epoch K, we have this nice L infinity guarantee that we said we should have. Okay, so it's saying that our effect function estimate should be close to the true effect function by 2 to the -k, uniformly in the nice X region. So what's the nice X region? The nice X region is everywhere that we've randomized in this epoch, excluding all of these isolated islands where we know there is no hope of being able to make good statistical guarantees. We can only make good statistical guarantees where we've randomized the selection of arms and we have enough data around us. We're not in these isolated, inestimable regions. Okay, so we know that GK should hold with high probability just by invoking essentially a uniform law of large numbers. Okay, and then we're gonna, using these 2 events, we're going to decompose our regret and then bound it. So we're also going to define the everything is good so far event, MGK bar, which is saying that up to epoch K, both many and good held. And then we're going to use it to decompose the regret as follows. So what is the regret of an algorithm? And here pi hat is referring to the algorithm I presented in the previous section. The regret up to horizon t is just the sum of instantaneous regrets at each little t, where the instantaneous regret is the difference between the expected regret that we would collect at this time period and the expected regret that pi star would collect in this period, conditioned on the covariates xt. By construction, this little RT isn't 0, 1. So this is exactly the regret. I just passed the expectations into the sum. And now what I'm going to do is I'm going to look at what epoch did capital T fall into. Call that epoch capital K of capital T. And all we're going to do is we're going to round up to also include this epoch. So we're going to see, where does T fall? Let's also include all the instantaneous regrets that remain in this epoch. And we're also only going to get a bigger number. So it's still an upper bound. And now we're going to use iterated expectations to decompose this regret, RT, conditioning on whether everything is good so far up to K minus 1, yes or no. Now, this expectation over here is bounded by 1, and this probability over here is bounded by 1. So I can take them away, and I still get a bound. Now I'm going to iterate this expectation on whether X fell into a randomization region or not. Okay, and now this probability over here is bounded by 1. So if I take it away, just replace it with the number 1, I still get an upper bound. So now I've decomposed the regret into 3 important components. One is the regret due to bad events, the regret due to the probability that something failed along the way. Not everything is good so far. The regret due to exploitation. So everything is good so far, and X does not fall into randomization region. And finally, the regret due to exploration. So everything is good so far, and X falls into a randomization region. So we're exploring. So what's the regret due to this exploration process? And I'm now going to bound each term by itself. So the easiest one is the regret due to exploitation. So essentially, we can show that if everything is good so far, then we've never made any mistakes when constructing the exploitation regions. Whenever we said arm plus 1 should be pulled in this region, we were always right. This set is a subset of the set of covariates where arm plus 1 or corresponding arm minus 1 are admissible. So this is easy to see in the regions where we've learned the right action, because we're always saying pull arm plus 1 when it's so positive that even when we add 2b, we don't get to 0. And by conditioning on everything good so far, we're saying those bounds held. It's a bit trickier to see in the screened out isolated regions. It's more of a geometrical argument that I don't have time to get into. But essentially, this is saying that the regret due to exploitation is just exactly 0. But what about the regret due to exploration? Well, why are we even in an exploration region at time t when everything is good so far? The only reason that can be is if the effect function is teeny tiny. Because if it weren't teeny tiny, then our estimate wouldn't be teeny tiny, and we would round it away from 0, and we would already be pulling one of the arms, arm plus 1 or arm minus 1. So the only reason that we're still randomizing is because the effect function is so small that it's hard for us to distinguish between arm plus 1 and arm minus 1. So if we look at this, we can now see that this first term, the regret, well, that's bounded by 2 to the minus k. And this probability is bounded by the probability that the effect function is small. Now, this probability is just a statement about the exogenously drawn random variable xt, has nothing to do with the history. We can remove the conditioning. And now we recognize that this probability is exactly what the margin condition controls. So we can upper bound it by 2 to the minus k to the power alpha. And once we compute what this sum is, we can find out that this is going to be some polynomial in capital T. So I'll come back to exactly what this polynomial is and what this exponent is, but let's just remember for now that this term, the regret due to exploration, just gave us some polynomial in T up to some additional polylogs. So it's O tilde of T to some power. Okay, and next, the regret due to bad events. So let me go through this quickly in the interest of time, so we'll get to look at the regret bound at the end. Essentially, what we can do is we can argue that the regret due to bad events is just going to be polylogs. So it's only going to contribute O tilde of 1 to the final bound. So what we saw is we had these 3 terms. Only one term actually contributed a non-negligible impact on the regret. So now we have this bound that says that if our instance satisfies all of our assumptions, beta smoothness, bounded density, shape regularity, and alpha margin, then the regret up to horizon capital T of our policy is going to be at most T to this power. Okay, this power is something that depends on all these problem parameters, alpha, beta, and D. First, before we dig into what is this thing, let's just ask, well, is this even the right? Question is yes. So we can also show that if pi is just any algorithm, not just the algorithm we just presented, then there's always going to be some instance that satisfies all the same assumptions, beta smoothness, bounded density, shape regularity, and alpha margin, with the same parameters to these assumptions, such that the regret of this algorithm is at least the same polynomial in T. Okay, there could be some mismatch in the polylogs between these two bounds, but the polynomial term matches. So putting these two things together, we have shown that the minimax regret is exactly of this order, up to polylogs. We'll put it another way, the leading exponent, which is what I'm calling the limit of the log over log t, is this thing right here. So what is this? This is just something that depends on the smoothness of these functions, beta, the sharpness of the margin alpha, and the dimension of the covariates d. And it's the optimal dependence on these parameters, as we've just shown. Let's try and kind of illustrate or draw out what this function is. So here I'm showing what this exponent is in different settings. So let's say that d is equal to 10. So we have 10-dimensional context variables, and alpha is equal to 1. So we're looking at the sharpest possible, or let's say sharpest interesting margin for this problem. When beta is equal to 1, we're just assuming that these functions are Lipschitz. So this is exactly the function that, this is exactly the problem that Rigolet and Zeevi studied. And indeed, this exponent here matches exactly that 0.86, whatever number that I showed in the slide in the beginning. As beta grows, we should be doing better because these functions are smoother, they're easier to learn. That's what we know, at least from supervised learning. So how does it translate to bandits? Well, indeed, our minimax regret exponent is going down as beta increases. As beta increases infinitely, this exponent goes to 0. So this is essentially saying that when beta is going to infinity and alpha is equal to 1, we're approaching a polylog regime where there's no longer a polynomial controlling the regret, but only polylogs remain. Well, that's exactly the result the Goldenschlager and Zeevi study got, right? So they were looking at the linear bandit only, linear response bandit. And what we're essentially saying that as beta increases, as we're getting more and more and more extrapolatable, the behavior that we're observing is approaching that of a linear response bandit. And indeed, Goldenschlager and Zeevi also assumed this sharpest possible margin. When the margin is slightly less sharp, we just get the same curve, but slightly different because now alpha is different. When beta is equal to 1, this is exactly Rigolet and Zeevi's result. They studied a variety of alphas. As beta increases, our minimax regret gets smaller and smaller and smaller in terms of its leading exponent. And as beta grows infinitely, we get some constant. Well, that constant happens to correspond exactly to what happens if you take Goldenschlager and Zeevi's problem, which is, nothing smooth, no beta going to infinity, just a linear regression function. And you take that linear regression function and you just assume a less sharp margin that Goldenschlager and Zeevi do, which was done in this Bastani et al. Paper. And whatever they got for a linear regression problem, that exponent exactly matches the limit of our exponent when beta goes to infinity. So again, we see that the behavior that occurs as we approach infinite extrapolatability is exactly the behavior in a problem with infinite extrapolatability. When alpha is equal to 0, that is, we're assuming no margin at all. We're not imposing any margin. Again, we get some other curve. We just plot out this function. And now when beta goes to infinity, we get this familiar 1/2. So why is 1/2 familiar? 1/2 corresponds to square root t. If you're somewhat familiar with the bandit literature, maybe you've heard about root t regret, which is exactly what shows up in a lot of these contextual bandit problems when you have a parametric form. So in a lot of the CS literature in particular, they don't assume margin conditions. So for example, the LinUCB algorithm for linear response bandits, they prove a square root t regret. So again, we approach exactly that. That's what we recover when we let beta goes to infinity and we go to this fully extrapolatable parametric setting. Okay, so let me wrap up and kind of offer some concluding remarks and think about, well, what are the takeaways? So we started by studying, well, what is a contextual bandit? And as soon as we defined what is a contextual bandit, what is this problem, it became immediately obvious that the regret in this problem should, of course, depend on how complex the underlying learning problem is. We're just trying to learn how would our actions influence outcomes. That's a supervised learning problem. If it's hard, our regret should be high. If it's easier, our regret should be low. That made total intuitive sense. But this intuitive seeming relationship was actually just hidden away behind either assuming these Goldilocks assumptions of everything is perfectly extrapolatable, the margin is as sharp as possible, which gave us logarithmic regret, or assuming just almost nothing, all hope is lost, forget anything, don't try to extrapolate, don't do anything, and you're going to get huge regret, right? So we tried to actually understand what's in between, and we did this by describing this smooth bandit problem, and we developed a new rate optimal algorithm that worked for any given beta parameter. And what this allowed us to do is, because we showed this algorithm was optimal, this allowed us to characterize exactly, or up to polylogs, that is, the minimax regret in terms of the key problem characteristics: the smoothness of the rewards, the sharpness of the margin, and the dimension of the covariance. Okay, so I'll end here, but if anybody has questions about post-contextual bandit inference, I'm always excited to talk about it.
Thank you, Nathan, for this really exciting and wonderful talk. And any questions from the audience about for Nathan? So while people might be composed, okay, yeah. So Zhaoqi raised his hand, so let me allow his to talk. Zhaoqi, I think you should be able to speak now.
Okay. Yeah. Yeah. Thank you so much for the talk. I have a question about your regime. So my question is, can you elaborate a little more on the last figure of the last slide, just to say how lin UCB fits into your regime? Because I've looked at that.
So I would start by saying it doesn't fit into this. I'm just kind of trying to say, what would the limit look like? So lin UCB is assuming that the conditional expected reward is a linear function. So we're not assuming that. But linear functions, as I've alluded to in the beginning, are these infinitely extrapolatable things. So they get root T regret, which is exactly what you get also in a multi-arm bandit problem without context when you don't assume a gap. So the minimax regret there is root T. So they match that root T exactly because it's not that much more contextual than a multi-arm bandit problem, because these things are infinitely extrapolatable. And all I'm pointing out here on the last figure is that in this setting where we make no margin assumption, right? So we're not really saying how far these arms can be from one another. It can be arbitrarily close and trick us all the time. In this setting, when beta goes to infinity, so we're approaching close more and more extrapolatability, because as beta grows, I'm essentially saying you can extrapolate farther and farther. And when beta goes to infinity, my leading exponent happens to go to 1/2. So it's kind of saying we're getting closer and closer to be in behavior to a problem where things are exactly infinitely extrapolatable, like lin UCB, which gets root T. I hope that's clear. Does that make more sense?
Yes, thanks so much.
Great. Other questions? So personally, I have actually a few questions. Really exciting talk. So I think in your method, I think you need to describe a couple of tuning parameters, right? The first one is the local polynomial regression. You have to tune it, and you also, in the case of you are trying to do this a discretization, the size also you have to tune it. I assume that in the local polynomial regression, you probably use the optimal one that's trying to trade off between the bias and variance. And then for the discretizations, I guess that would depend on the beta and other and T, I guess, right? Like the sample size, so that you know what's the optimal way. And I think here the rate you are obtaining is that you're assuming that you are choosing the optimal scenario so that you can obtain this rate, right?
Exactly right. So you highlight something really important, which is that my algorithm knows beta. So the first thing I would say is in some sense, that's what it's supposed to know beta, because if we're talking about minimax regret, we're talking about inf over pi, sup over problem instances of the regret. So the inf player doesn't know what the sup player will pick, but it knows the feasible region of the sup player. If we said, it can pick any beta at all that will happen is minimax regret will be linear in T. So it's not interesting. So the way to talk about unknown beta is slightly different. So just, in terms of minimax regret, if I want to compute it, I should exhibit a beta dependent algorithm. Now, what does it mean to not know beta? To not know beta wouldn't be minimax regret with respect to all possible betas. It would be something like, consider script P sub beta for every beta. It's kind of this nested class set of classes where for larger beta, it gets smaller. And then I'm going to say, I choose some problem instance in its union, and I want an algorithm that achieves the minimax regret corresponding to the smallest class that contains this instance. So it's kind of a convoluted definition. And for this to make sense, you have to define minimax regrets first, because you can't just say adaptive to the instance, because the minimax regret adaptive to the instance is 0. It's just play pi star. So you have to say, I want to be adaptive to beta, but not to other things in this instance. So it's sort of hard thing to say, what does it mean to adapt? But the answer to how to adapt is kind of interesting. It's sort of easy. It's either possible and easy or impossible. So if you assume nothing, it's impossible and you cannot adapt. If you assume self-similarity, so essentially saying that no matter how far you zoom into these functions, they always look beta smooth, no matter how far you zoom and where you zoom in. If you assume self-similarity, then the answer is you're going to explore at random for some amount of time in the beginning that is going to be of order lower than the regret. And then at the end of this warm-up period, you're going to fit functions and learn beta, and then you're going to play this algorithm as though beta is known, and that will be adaptive. And that's highlights sort of interesting nuance in these bandit problems, that it's not really just supervised learning like I was trying to say. It's really not, because it's more than that. Because if you were just trying to do optimal MSE, you are talking about choosing these parameters optimally, you can actually do adaptive optimal MSE in the offline regression problem without knowing beta, without assuming anything. I think, for example, in Lasso 2, you can choose without knowing the sparsity. What you cannot do is you cannot do adaptive confidence intervals. If you want to do uncertainty quantification, you need to assume self-similarity. And that's kind of interesting, the connection here, why this same sort of dichotomy appears here, because indeed in bandits, it's not just about supervised learning. It's also about uncertainty quantification, because you need to know, I need to learn these functions, but I also need to decide, have I learned them enough to exploit, or do I need to explore more? And if you don't know that, if you're not able to quantify that, then you cannot get minimax regret. So indeed, it's a bit more nuanced in that. But anyway, that's how you would adapt in this problem. And that's how you would deal with unknown beta.
I see. Great. Other questions? Okay, I think everybody's excited about the weekend. So okay.
Yeah, it's like 7:30 over here, and instead of my
true.
glass of wine, I had a cup of coffee.
Yeah. Okay. So if no other questions, then let's thank Nathan again for this really wonderful talks. Yeah, it's very, very good, very insightful. Yeah. And thank you so much, Nathan. And thanks everyone for attending. And I wish everyone to have a really great long weekend. Thank you.
Good weekend, everybody. Stay safe.
Thank you.
Thanks for having me.